So now what I'm going to do is I'm going to go over a powerful technique for solving for derivatives that otherwise look like they might not be solvable. Okay, and it's called logarithmic differentiation, and it utilizes our logarithm rules in order to actually go find the derivative of some pretty complex functions. All right, so here's what logarithmic differentiation does. We'll start out with number one, which is we're going to take the natural log of both sides of the equation. Okay, then two. All right? And then we'll use the laws of log to simplify the equation. Then three, we're going to differentiate implicitly. So we're going to use implicit differentiation with respect to x. And then we're going to solve, finally, for the resulting y prime. So that's the process that we're going to use, right? First, we're going to take the natural log of both sides, all right? Then we'll use the laws of log to simplify the equation. Then we'll differentiate implicitly with respect to x, and then we'll solve for the resulting y prime. Let's take a look at a pretty simple example, okay? But one that'll kind of like allow us to see that, in fact, we use the laws of differentiation in order to find out all of our laws of differentiation, right? That's the proofs oftentimes will utilize other rules for taking derivatives. So let's say, for example, I want to prove the power rule. That is that, right, the power rule tells us that d dx of x to the n is going to equal n x to the n minus 1. Okay? Well, what I'm going to do then is I'm going to say, okay, well, let's take the natural log of x to the n, right? So we're going to say that y equals x to the n. And then we'll take the natural log of both sides, right? So we'll do number one right here. So this is going to give me natural log of y equals natural log of x to the n. Okay? And then what I'm going to do is I'm going to use the rules of logarithm, right? Okay, to pull out that n. So now I've got natural log of y is going to equal n times natural log of x. All right? Now this is important to notice that n here is constant. N is constant. So when I go to differentiate implicitly, do number three, I'm going to get 1 over y times dy dx is going to equal, and this is just going to be n times 1 over x. So what that's going to then give me is that's going to be dy dx is going to equal n over x times y. Well, what's y? Remember, y is x to the n. So dy dx is going to equal n, dy dx equals n times x to the n over n, or x to the n over x, excuse me, which equals n times x to the n minus 1. And we have proven our power rule. And there you go. So you can actually kind of see how kind of powerful this is, right? We started out first, we took the natural log of both sides. Then I simplified, right? And this is one of the most common simplifications, right? Basically, you're just gonna pull out the n, or pull out whatever the value is, the constant value is, okay? Not constant value, but whatever the power is, right? And then I utilize my rules of log. I mean, in this case, it's basically a constant times the natural log. So I just multiply that. Then I simplify, right, by bringing over my y, just like I would do in any other implicit differentiation. That's it. Let's take a look at another example. Let's differentiate now. We're going to take, we'll let y equal, and we'll call it b to the x. Okay. Now b is constant. We already know what this is going to be. Okay. But what I'm going to do is I'm going to utilize this logarithmic differentiation in order to do it. Okay. So I'm going to take the natural log of both sides. So ln of y equals ln of b to the x. Then I'll pull the x out. Okay. And so that gives me x ln of b is equal to ln of y. Then, right now, differentiate implicitly. Now b is constant, so the natural log of b is also constant. Okay, so the natural log of b is also constant. Differentiate implicitly, what I get is I get 1 over y times dy dx equals, and this is just x times a constant, so this is just going to be the natural log of b. So now I'll multiply both sides by 1 over y. So I get now dy dx is going to equal ln of b times y, which is equal to ln of b, or is equal to b to the x times ln of b, which is exactly what we expect to get. All right. Notice the difference between this particular one and the power rule is which value is the constant. In the case of, right, taking the derivative of the exponential, the base is constant and the exponent is variable. In the case of the power rule, okay, the base is the variable and the power is the constant, right? So actually different constants in each case. So be careful with those two rules, okay? They look pretty similar sometimes, and you want to make sure, right, you're asking yourself, well, which is the constant, which is the variable, okay, to differentiate between the two. Now let's look at a more complicated example. Suppose that we have, so this is example number 3, we have y equals x to the square root of x, okay? Well, now we're going to use logarithmic differentiation. The reason why I know that is because I've got a function as my variable, and I have a variable in the base. These ones, there's no way to go about doing this without doing logarithmic differentiation. You kind of look at it and you go, okay, that's what I should use, logarithmic differentiation, right? Whenever I have a variable to some kind of function with variable in it. All right, so what I'll do now is I'll take the natural log of y to both sides, and that'll be the natural log of x to the square root of x, okay? So now using the laws of logarithm, I get ln of y is equal to the square root of x ln of x, okay? Now when I differentiate implicitly, okay, my next step here, what I'm going to get now is I'm going to get 1 over y dy dx is going to equal, and now I've got to use something, I've got to use the product rule. So this is going to be 1 over, it's 1/2 times x to the negative 1/2, which I'm going to rewrite as x to the 1 over x, or 1 over the square root of x, times ln of x, okay, plus the square root of x over x, okay. Now I'm going to do a little bit of simplification here on the left-hand side. So 1 over y dy dx is going to equal, and this will be 1 over 2 root x plus, and this will be 1 over the square root of x, okay? Square root of x divided by x, that's going to end up being 1 over the square root of x, all right? And this then is going to equal 1, this is ln of x. ln of x over 2 root x plus 1 over root x. It'll then give me ln of x plus 2 divided by 2 root x. So basically just finding a common denominator of being 2 root x, right? Multiply the top and bottom of 1 over the square root of x by 2, add the two together, okay? So now I'm going to solve. I get dy dx is going to equal y times ln of x plus 2 over 2 square root of x. And this is thus going to equal x to the square root of x times ln of x plus 2 over 2 root x. And there we go. All right, same process each and every time. One of the things I noticed, hey, this would be really nice to use logarithmic differentiation because I've got a function in my exponent. Now let's look at an example where it just might make some sense to use logarithmic differentiation because it makes the problem a lot easier. Okay, sometimes, we can actually differentiate using quotient rule, power rule, chain rule over and over and over again, but maybe logarithmic differentiation is going to make it easier. So here we have an example, okay, and it's going to be y equals x to the 3/4 times the square root of x squared plus 1. And we'll divide that through by then 3x plus 2 to the 5th. Now what I'm going to do is I'm going to take the natural log of both sides, just like with logarithmic differentiation. So I have ln of y equals now the natural log of x to the 3/4 square root x squared plus 1 divided by 3x plus 2 to the 5th. Now, here's where knowing your logarithm rules comes in kind of handy. This thing here then, okay, just we're talking about now the left-hand side, is going to equal the natural log of x to the 3/4, okay, plus the natural log of the square root of x squared plus 1, okay, minus, and notice that this is all in parentheses, the addition. I guess it doesn't matter because it's addition, but then we're going to subtract the natural log of 3x plus 2 to the 5th. Okay? Now we can actually further simplify this. This is going to be 3/4 ln of x plus 1/2 ln of x squared plus 1 minus 5 ln of 3x plus 2. Okay? Now we've got some rules that we can utilize here that makes this a lot easier. This is going to be 3/4 times 1 over x. Okay? So now we'll take, by the way, we'll put this in here. So now we're going to take the derivative of both sides. So now we'll differentiate. Now that we've got these. All right, so we get 1 over y dy dx, okay, equals, and this will be 3 over 4x, right, because natural log of x is just 1 over x, plus, and this is going to be the derivative of the inside, so this is going to be 2x divided by 2 times x squared plus 1, plus, minus, and this will be 5 times 3, right, because the derivative of 3x plus 2 is just 3, divided by 3x plus 2. Okay? There we are. Then all we got to do is multiply both sides by y. We get dy dx is going to equal, and yeah, I know it's a bit of a mess, but at least we have a derivative now, x to the 3/4 times x squared plus 1 over 3x plus 2 to the 5th times 3 over 4x minus, plus 2x over 2 times x squared plus 1 minus 15 over 3x plus 2. So getting to that derivative now, heck of a lot easier than going through and utilizing multiple chain rules, utilizing multiple power rules, and using a quotient rule inside of that. The logarithmic differentiation just makes this a lot easier to work with. Okay? So this actually completes our mini lecture on logarithmic differentiation. It's a really powerful technique. It's one that you're going to want to use and going to want to learn. It's going to show up a lot more inside of all of your sections. Okay, this completes the lesson.